Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. Today we will be looking at the shortest path algorithm, and later on in this lecture we will be looking at the Dijkstra's algorithm. So, we have been given a graph which has n vertices and some set of m edges, and in set of basic definitions we have that if u v is in the edge implies v u is in the edge, then we call this one as the undirected graph, and a weights can be assigned to each edge. In this case we call it an weighted graph. For every vertex v, if there exists an edge from u to v, then we say v is an neighbor of u or v is adjacent to u, and the total number of neighbors of u is known as the degree of u. So, here is the example. We have a set of vertices which we represent as circles in this plane, and the edges are represented as lines between the corresponding two vertices. So, here is an undirected graph, which does not have any edge weights, and we have these lines which indicate the edges. We can also have the weights on the edges, and this we call the weighted undirected graph. We can also have this one directed graph in which each edge is represented by an arrow. So, here a arrow G E implies that G E is an edge and E G is not an edge. So, mathematically these graphs are used for expressing relations between objects. It is simple, it is general, and at the same time it is used for a lot of applications. In particular, lot of real life problems can be modeled as graph theory problems. So, understanding graph algorithms is a very essential part of the subject of algorithms. So, in an undirected graph we say that u is connected to v if there exists a path from u to v, and in an undirected graph if there is a path from u to v, there is a path from v to u. In the case of directed graph we say u is connected to v if there exists a directed path from u to v. Now, what do I mean by path? So, here is a graph, and this is a path of length 4 and a directed path. The length is the total number of edges that occurs in this path. We can have also have the smaller path which are like this of length 3, and length of a path is the number of edges that occur in a path, and the distance between any two vertices is the length of the shortest path between these two vertices. You can think of this one as a map of a city. So, you have these various nodes and we have the edges, and the question is how many roads we have to take to reach one vertex, one place to the another. And so, the question that one has to ask is that what is the shortest distance of u from v, and rather we can also ask what is the shortest distance of any vertex from v. So, we are at a vertex v and we say that it is my home and I want to calculate the shortest distance of all interesting places in this city from my home. We have seen this problem and we solve it using the breadth first search algorithm. Now, in the breadth first search algorithm, what we were looking at is that the distance between two points, least number of edges that we want to traverse to go from point A to point B. If you think of it realistically, in the case of maps, that is not the case, correct? You have your home, and from that you want to reach some museum which is far away. Now, there are various important landmarks in the middle. Maybe you have to go to one particular signal, then from there you have to go to another junction and so on. Now, the distance from your home to the signal is need not be same as the distance from the signal to the next junction. So, there must be some kind of a weight, which in general in the case of maps we represent it as a distance. So, each edge we can represent as a real number, and these real numbers can mean many things. In general, it can mean the distance that I am talking about in the case of maps, but this real numbers can have lots of other interesting usages. For example, the amount of traffic flow and so on and so forth. So, a weight can be the amount of traffic that going from point A to point B and like that. In fact, these numbers can also be negative. So, when we have been given the edges, various real numbers have been assigned to various edges, then the length of a path is the sum of the weights on each of the edges in that path. It is no longer the number of edges in that path, sum of the weights of edges in this path. And the shortest distance from a vertex to another vertex is the length of the shortest path. It seems kind of very natural. For example, say here is a weighted graph. Now, in this weighted graph I have to go from G to A, and when I have to go from G to A I can take this path. Now, note that what is the length of this path? Length of this path is 9 plus 5 plus 8 plus 7, and turns out to be length of this path is 29. So, although the number of edges is 4, the distance is 29. We can improve it and say that okay, maybe there is a shorter path and say let us take this one. And this is of course in the original set we have just 3 edges that are going from, we just need to go along 3 edges to go from G to A, but the length becomes 9 plus 7 plus 7, which is 23. And if you look at it, there is another edge, another path which has just 3 edges, and the length is 11 plus 6 plus 5, which is 22. So, the interesting part here is that it is no longer dependent on the number of edges that are being used, it depends on the edge weights. Of course, the goal is to find the shortest path. What one might think of is that okay, I start from G and let us take the closest signal or junction or next node that you can think of is, in this case it is a distance 9 and here it is a distance 11. So, let us take the shortest path. So, I go here, but then it says that oh here are 2 edges 7 and 5 and 15, I take the shortest path which is 5. So, this kind of a greedy approach will not work, it is nothing new, we know that very well. If you have to go from our home to somebody else's home, it is not about the which road will I get the signal earliest, that is not the question at all. The question is what is the sum of the total number of distances. So, this is the case of the paths in a weighted graph. The weights can also be negative. Now, one might ask how can the weights be negative? A distance cannot be negative. You are right, but as I told, in the case of graphs, graphs can be used for representing various combinatorial objects and various real life problems. And in many real life problems, we want to put a negative number there. So, there are sometimes some reasons for it, some negative flow going from one direction to the another and so on and so forth. So, one can ask the same question. So, here in this case say I have this negative, this edge has this negative weight. Now, let us see what happens to the shortest path between G to A. Again my longest path that I can think of was 29, the next path remains same 23, the earlier shortest path was 22, but note that if I go along this edge, this path, I go 9 minus 5 and plus 5. So, the edge becomes, this path becomes shortest. So, this negative quantity can contribute to getting the smallest path between 2 points. So, is there any problem in this whole negative thing? As such, no, but what happens if I can get a cycle which is negative? So, we call a cycle a negative cycle if the sum of the weights of all the edges in the cycle is negative. For example, look at this graph. Here I have made this vertex also minus 9. So, if I go along this path is minus 9 plus 5 plus 2, which is minus 2. Thus, this cycle is minus 2. So, if I want to go from G to A, one thing that one can do is I can take this round and then again this round and then again this round and then again this round, and I keep on doing till I hit as low as quantity I want, and after I have come to this point after many steps, I then take a path from there to here. But clearly there is some problem here, that the distance from G to A in that case minimum distance is minus infinity, because for any number you say I can take that many number of rounds and push the total distance lower, because every time I go for one round the distance goes down by minus 2. So, first round, second round, third round, fourth round, and there is a minus 8 plus 7 plus say is just plus 6. I can repeat this 100 times and I get minus 200 from here and I have plus 14. So, minus 184. So, I can go push this one to any low number. So, while negative numbers are fine, having negative cycles is a bit of a problem. So, the usual assumptions that one has in this case is that we do not have negative cycles, and sometimes we also assume that we have no negative weights. Now, although as I told you negative weights are important and we will come to that possibly next lecture, but in the today's lecture we will be considering the case when there is no negative weights at all. So, problem of finding the shortest path, we have been given a graph with positive edge weights. Let us the weight of the edge V 1 V 2 be given by W V 1 V 2, and we have to find the shortest path from U to V. Problem is simple and clearly well motivated, and we have to understand. So, what is the idea of the algorithm? Let us see the first algorithm that we can think of. I want to find the distance between my home and the museum. Now, what I do? I am a lazy person. So, I do is that I ask my neighbor, what is the distance from your home to the museum? He says something. I ask my next neighbor, what is the distance from your home to the museum? He says something. And then after I have got the information of all my neighbors, then can I make a decision? For example, say I find the first neighbor whose home is at distance 1 kilometer from my home, and he says that his house is at distance say 8 kilometers from the museum. So, it means that if I go along, first go to his home and then go to the museum, then it will take me 9 kilometers. Similarly, if I go to the other neighbor and I say that okay, that person says that oh, distance between my home and the other neighbor's home is just 2 kilometers, but the distance from his home and the museum is just 5. It means that the total distance if I go via his home is 7. And similarly, I take another neighbor whose house is at distance say 4 from my home, and she says that her house is at distance just 1 from the museum. So, if I go through her home, it will take just 5. So, that means that all I need to do is that I have to exhaust all possibilities. I have to look at all the possible neighbors, ask them how what is their closest, what is the distance of their home to the museum, and accordingly I will get the answer. So, using this idea, can we construct an algorithm? So, we will take a small break now. After the break, we will continue with this. Welcome back after the break. Before the break, we are looking at finding the shortest distance from a point to another point. So, as we described the algorithm, so let us say if I look at all my neighbors, if V 1 W 1 V, W 2 V, W k V be the edges into V, I first ask what is the distance of u to w1 from u to w2 and u to wk and write them as dw1, dw2 to dwk. Now, I know that if I have to enter v, I have to enter through either of these paths. I have only finite number of places through which I can enter. I know that these are the places. So, if I enter through w1, what would be my distance? My distance will be d of w1, which is the shortest distance to w1, and the weight of this edge, which is w of w1 comma v, and similarly for w2 and so on. And if I take the minimum of all of them, I would get the shortest distance from u to v. So, I do that minimum for all the I between 1 to k, the distance of wi and the distance from wi to v. Now, this is a recursive kind of algorithm in some sense. So, this idea is that I have to find the shortest distance from G to A. Instead of looking at A, I say that okay, A can be entered through either B or D. I say okay, what is your D? What is D of B? And say I somehow have understood that D of B is 16. Similarly, say I ask what is D of this vertex, and say this one is 17. And what I know is that now if I take this route, I have 17 plus 5 is 22, and if I take this route 16 plus 7 is 23. So, I will take this route, and this is the best that can imagine, because I have to enter either through this or through this, and if I enter through this, then of course, it has already told me, it has given me the right answer. So, under the condition that my neighbors have done a good job, I will get the right answer. Now, for finding this distance, I can even also imagine that see, please remove me out of the whole picture. So, I am not there. If I remove me out of the whole picture, then what is the distance from G to U? If your shortest distance is via going through me, then does not help me at all. So, if you do not go through me, then what is the shortest distance? So, this is the kind of the recursive kind of algorithm, right, where I have reduced this graph size by 1 by removing me from this picture, and I am asking solve the shortest distance from G to D in a smaller graph. Here is the pseudocode. For every vertex in the neighborhood, the set of vertices that are entering W, you first find the distance of u from that neighborhood, and you remove that vertex v from that graph and output the shortest distance, and you add this one and you take the minimum of that. This is exactly what I explained just now. This is perfectly fine. This is exactly the recursive algorithm that we had looked at so often, so longer, kind of a divide and conquer approach. It is a recursive algorithm, except that let us try to understand the runtime. So, the correctness of the algorithm of course follows from the fact that the shortest path from u to v must enter through one of the incoming edges, and the shortest path that enters through v u, then the distance from v to u must be exactly this. So, the short distance of dv will be dw plus this one, which is the edge weight of w v. So, if we represent T n to be the complexity for finding time complexity for finding the shortest distance between two vertices in a graph of n vertex, then what is T of n? Note that in the worst case, a vertex can have n minus 1 neighbors. If it has n minus 1 neighbors, then this is T of n. Now, this G new graph that I input is a size n minus 1. So, it is n minus 1 times T n minus 1, and if you do it again, this n minus 1 times n minus 2 times T n minus 2, and you keep on doing it, it is n minus 1 factorial. So, the run time of this algorithm that I described is an n minus 1 factorial, not good at all. You can prove that this object is bigger than 2 to the power n. It is a massive number. So, can we do better? Idea is that can we reuse the computations? Like, since it is a graph structure, we might be able to reuse it in some interesting way. Say for example, let us see, we want to find the shortest path from G to A. So, what do? The first thing is that what is the closest vertex from G? In this case it is E. Say let us take E, and I claim that the distance of E from G or from E from G is just 9. Why? If there exists some other path, say this path, which is shorter than this path, since I am looking at only positive numbers, positive weights, so in that case this edge must have been less than this this edge. Weight of this edge must have been less than the weight of this edge, and in which case we would have chosen this edge first than this edge. So, at any time I first say that the distance at this moment I do not know the distance of A from G from this one. I will first put infinite at all of these places, then I put 0 here. So, this 0 indicates that the distance of G from itself is 0. If this is the distance of G from itself, then what is the distance of E from G? Now, the distance of E from G is not infinity now, it is less than infinity. It is the shortest distance I can think of, which is 9 here. So, I can erase this part and I can write 9 here, and again here, since this is a direct edge that is there from F. So, F says that okay, I can take this edge, and in that case you can get from G to this one. So, I can also distance from G to F will be 0 plus the edge weight, which is 11. So, at this stage this says that see all these vertices has distance infinity from G, whereas this vertex has distance 9 and this vertex has distance 11. So, at this point take the closest vertex, which is 9, and I claim that this vertex has to be, this distance is the shortest distance of E from G. Now, at this point this becomes the shortest distance. Now, this is fixed. Once I color something red, means I know the shortest distance from G to that vertex. Once I know the shortest distance from G to this vertex, what can we say? This vertex, say C, it was at distance 1 from E, because this edge was going, and this is 9. So, this infinity goes down from infinity to 10, 9 plus 1 10. So, in other words, it is something like it is a distributive kind of algorithm, but somebody is saying that see I have found out a shortest path from my place to somebody else to the museum at a distance 10, and then I said that oh see I have an edge to your place at distance 3. Oh, that means now I can say that I have a short path of length less than 10 plus 3, which is 13. If that is smaller than the path that I had in mind, then I will say that okay, now I know that this is my current shortest path, and I keep on doing. As soon as somebody updates their own information, I can update my information. So, similarly here say E have updated its information to 9, I am at distance 7 from E. So, my distance, I have a path whose distance is just 16, 7 plus 9, and similarly D says that my distance now becomes 9 plus 5, which is 14. At this stage C says that see my distance is 10 from your place, it is 14 for D, B is 16 and F is 11. So, C says that see since I am the shortest right now, so I can claim that my shortest distance from G is 10. If there exists some other shortest distance, then there will be another edge that I would have chosen before. So, at this point I choose this edge E. Once this gets updated, now C is updated. C says that okay, now I have found out that my shortest distance is 10. Then B says that oh okay great, I have a path from C to B which is 8. This one will give 18, and B will say that I already have a path of length 16 through E. So, I will not care about this path through C, and this path is also useless because this G says that I already know the shortest distance from myself. So, at this point it says that okay, now again we have these 3 things, and F says that okay, I am the shortest, and so we will pick F. Again at this point the shortest distance d will try to update itself and says that okay, if f's distance is 11, then I have a path of length 11 plus 6 which is 17, but 17 is greater than 14. So, again not good. So, again I will not update it. So, at this stage we have two of these vertices, and now since d is minimum, so d says that we pick d, and after we pick d, then we will update a to 19, and at this stage 16 and 19 will take 16 from there. Similarly, we will take 19 there. So, this will give us the algorithm for finding the shortest path. So, one thing to note is that we are reusing computations, and just like I was writing down these things on the top, I need to write it down somewhere. Now, where to write it down? So, usually we write it down in a table. So, we can think of this one as something like this one. We have a graph, we have a table, on top of that we have this set of vertices, and we start with say this g, and as soon as we see g, of course, we start with everything being infinity here, and as soon as we make any one of them to be red, we will erase this part and we will update it to 0, and we take the next one, and the next one again we say that okay, the age is 9 plus 0. So, we will update this one to 9 and so on. So, in other words, if we keep on doing this, we will be able to find the shortest path from G to A. The pseudocode for this algorithm is, we for every vertex we first write the distance to be infinity and the source has distance 0. We have q to be equal to the whole vertex set. Now, while this q is not empty, we pick a element which is the smallest distance in this set of vertices. We remove that element from q and we update all its neighbors. How do I update? For all neighbors v of u, we write down the dist as whatever the current dist is and minimum of dist of u with this edge weight. This is a very simple and beautiful algorithm, and this is known as the Dijkstra's algorithm. So, one thing to note is that what is the running time of this algorithm? So, note that finding the minimum takes order v steps, updating the distance takes order v steps each round, because we have to update all its neighbors if possible, and there are v rounds, where every round is taking up one element out of the queue and removing it, and so the total runtime is order v square. So, we have to find the shortest distance from u to v in order v square. In fact, you can see that this can be used for finding the shortest distance from u to any vertex in order v square, and this is what is known as the single source shortest path problem. It is one of the very important problems in this field. Although we have given the runtime of v square, using slightly more clever data structures called Fibonacci heaps, one can get improvement to order e plus v log v. Note that order e is in general less than v square. So, this is slightly better than order v square, although we will not go into this implementation of this step at all in this series. So, this brings us to the end of this lecture. In the next lecture, we will be looking at more graph algorithms. Thank you.